So it's a pleasure. It's always a pleasure to work in capacity building, to empower, mentor others. And yeah, thank you for creating this platform where we can do that. So before I dive into the subject matter, I think it's important you know who I am. And Dr. Kate asked that maybe I tell you a bit about my journey into research. Yeah, I'm Dr. Joseph Siwefojo. I'm a medical doctor first by training. I did my medical studies in Yaoundé, Faculty of Medicine and Biomedical Sciences. And I finished, and I was sent to a very rural and bushy place to work as a medical doctor. That was in Bangasina, okay, somewhere in the Mbam. Yeah, just a short story on myself. I had got into research. While there, I saw there was a lot of epilepsy. Epilepsy was very, very common. I mean, I remember my first days in that village. You could walk on the road and see people having seizures by the roadside. So it was pretty concerning. And yeah, I went to the community. I tried to look into it, like, why is there so much epilepsy? How are they taken care of, and so on. And I put in place a system, an epilepsy clinic, to care for these people. I put in place a community kind of setup, you know, to be able to track them in the community, sensitize people about the disease, that they should not stigmatize these people, and so on and so forth. And in doing all of that, I connected with Professor Njamshi, who was my lecturer. He taught me neurology back in school, and yeah, I knew him at that level. I can't say we had a personal relationship. So I came to Yaoundé one day, and yeah, through the help of some seniors or Tongaka and so on, who were working very close with him, I got to meet him. I asked, I want to see him, and they arranged that. I entered his office and said, okay, sir, I am Dr. This, and I am working in this place and lots of epilepsy. I've seen that you've done a lot of epilepsy work, you know, in your research and as a neurologist. And yeah, there's something I want to put up there. I just want you to coach me, to mentor me on this. And he agreed. We exchanged numbers, emails, and he said, okay, I'm here for you, do it. And yeah, I'm here, I'm okay with that. So I started following up this people epilepsy, and I will send him monthly reports. At the end of the month, I would just say, okay, sir, this month I saw 50 persons with epilepsy. I had this challenge, this person was not responding to this drug, this person had this kind of seizures. And I was doing that at times even with pictures and stuff like that. And eventually a project on epilepsy came up. He was contacted by a Belgian partner, a Belgian collaborator in research, who told him, I want to do some research in epilepsy in Cameroon. He was doing many African countries, but he said Cameroon is one of his sites of interest, okay? And yeah, they made the arrangements, and the Belgian collaborator came to Cameroon, and he said he wants to go to some rural places to investigate about epilepsy. And so Prom Jamshi told him, I cannot go with you right now because I'm busy in Yaoundé, but I can connect you to someone in the field who can help you out. And that was me. So he got to me and said, okay, are you free? I'm sending someone your way. Please just help him. He has some work to do on epilepsy and all of that. So I met with him, and he came to the villages, connected, and we went around, did some surveys, door-to-door surveys, screening epilepsy, examining people with epilepsy. Yeah, and at the end of a couple of days, we worked together for about a week. At the end of that period, he got close to me. He was like, you're very good at this. Like, what is your training? I said, I'm a doctor. You have never done research? I said, no. Then how do you know so much about epilepsy, about research, about... I said, well, I've been doing this, and I've been doing online classes, and I've been educating myself on this. And right there in the bush, he told me, I want you in my team. I want you to do a PhD with you. I want you to be my PhD student. Yeah, and that was it. I had no publication. I had no research background. Yes, I had a lot of research interest. I had a lot of self-tutoring in public health, in epidemiology, through Coursera and other courses online. But I really had no proof, no results to show forth. And he said, you have it in you. You have just not had the opportunity. I think we can work together. Yeah. He went back to Belgium, sent me the invitation letter, the contract with the university assigned, and yeah, a couple of weeks later, I began my PhD with him in Belgium, and it was a great experience. We got to work a lot, publish a lot. And yeah, I completed and came back to Cameroon, where now I'm working as a researcher with the Ministry of Health. I work in the research division of the Ministry of Health. And I'm also doing research with Professor Jamshi and his team. We do quite some work in the rural places where I come from. Yeah. So basically, as this, I'm just joining my voice to Dr. Aguns and others, maybe who have spoken before, to let you know that research is not taboo. It's something you can grow into. It's something you can develop and yeah, and really make a difference. It's not for a select few. If you have the interest, of course, not for everybody. Not everybody will like it, but if you have the interest, you're already graced to know some of us. You know me, Dr. Kate, and so on. You can get close to us and like, I have this interest and so on. We can channel that energy and you can make something good out of it. So don't be scared. Don't be skeptical. It's doable. And in fact, the opportunities are wide open. Okay. There's enough space for everybody if you want to do research in our setting. All right, I think that's it. Yeah, before I jump into the topic matter, there was a question. Okay, Dr. Kate has already responded. I saw a question about, can you submit to more than one journal? No, it's not advisable. Okay, it's a big no. It's even to an extent intellectual fraud, okay, to do that, because it seems like you want to get published in 2-3 journals for the same work. Generally, what is done is you submit to the best, the number one on your list, maybe Lancet. If you think that work is good enough, you begin with a big journal, and until you get a response from them, you don't have to submit it somewhere else. If that big journal takes it, fine, you're good. If they reject, you go to your second choice of a journal in that same domain, and so on and so forth. Okay, I've submitted sometimes to about 3 journals. I'm very ambitious. At times I'll go for you start with Lancet or New England. They said, no, this is not really what we want. You go down to maybe I don't know, BMJ, and then go down to BMC and stuff like that. And then someone will take it eventually. And of course, the comments at times we get along the line also help you to improve the paper, because they won't just say no. At times they will actually review it and say, improve this, improve that, this is not good enough. Yeah, and you build that up. So please don't submit to 2 journals at the same time. In fact, in the submission process, they expect you to tick a box saying this work has not been submitted elsewhere at the moment. Okay, otherwise it won't even be considered by that journal. Yeah. So I think I wanted to say that before I jump into what I have at hand. Great. As Dr. Kate said earlier, we'll be discussing about statistical methods. Okay, statistical testing in your data, because it's a crucial part in research. You can have a good idea, you collect data, but how you sell it really depends much more on how you analyze it. You have the information, how do you put it together? How do you present it? What relevance and interpretation do you bring out from it? Are you using sound and accepted methodologies to bring those conclusions and so on? So that's all about your study design. Is all about your statistical analysis. And it's important you know that it's a whole world on its own. I don't even have a PhD in statistics. I have a PhD in epidemiology, so I can't brag to be a statistician. It's a whole world on its own. Okay, so but I'm going to give you the basics, share with you a few thoughts, which will put you on in the right direction, and you'll be able to build on it. Okay, one thing you should know about research is that it is a lot of self-tutoring. All the classes you will attend, all the things you do are just to point you in a direction, and then you build the skills by doing. The more you do, the more you correct yourself, you adjust, you perfect your technique and your feeling about the research. So I hope I'll be able to do that in the light of statistics. So I'm going to share my screen. Okay, can we see my screen? I hope. Statistical tests. Tokate, can you please confirm? I want to be sure that.
Yes, we can see your screen. Brother, nice and clear, nice and clean.
Yeah, thanks. Thank you so much. Yes, so we're going to be talking about this for the next couple of minutes. I just want to say If along the line you have a question, a concern, please, I want to say raise your hand, but I may not see. You can unmute your mic and interrupt me. You're allowed to do that, okay? I believe it's when something is very hot, it's still boiling in you, that you can easily catch the answer.
Yeah,
wait
Joseph,
till the end,
if they raise their hands, I can see and I can moderate that from this end.
All right, thank you. But the point I'm passing is I like to address things along the line. At times at the end, it could be difficult. You may have even lost the exact thought that you had. And yeah, it's just my style. I hope the moderators don't have a problem with that. Of course, it's included in my time. It's not an extra time. I've taken that into account in my presentation.
That's okay.
All right, thank you. Yeah, introduction. Okay, keyword is introduction. Because we will not go very far if I have to get an exhaustive lecture on statistical tests. All right. Yes, we're going to follow the plan that you see on your slides. We'll say a few things about type of variables, a few things about things you should consider before you analyze. Okay, we're going to talk about how to test for one continuous variable, two continuous variables, three or more groups, and so on, and then have a summary at the end, a kind of take-home message of what we would have discussed. All right. Like I said, this is a very basic presentation, okay, to just help us understand which test is appropriate for what type of data. Because you're going to collect lots of data, maybe during your thesis, because this is really oriented about from thesis to publication. So maybe during your thesis, you collected some data and yeah, you had some nice slides during the public defense and had some good marks, probably maybe defended already, you're out, or maybe you're still working on it, I don't know. But you should understand that the kind of data you collect will condition the kind of analysis that you can do with that data. So it's important you understand it right from the start, okay? Else you are going to miss a lot of things. The aim is about you building an intuition about how to analyze data. And to also, when you understand how different statistical tests are done, you will be able to critically assess, to critically examine what other scientists report. Okay, at times you see an article, and not many people skip the section of statistical analysis or just read methods. I did this, I went to the community, I collected samples, I came out to the lab, I did this and that, and then there is statistical analysis. They're like, this place is so boring and complex. You just skip the results. Okay, I hope that at the end of this exchange, you'll be able to read that paragraph of statistical analysis and make sense out of it, not as a specialist, but understand at least what the authors did with their data and what to expect in terms of results. Okay. And I wrote here some decisions will be taken by rule of thumb, but remain flexible. Rule of thumb is simply like a law that you apply. Like when it's like this, I do this. Okay. For starters, that is the best way to go about it. Don't overcomplicate, don't get into mathematical equation, quod error demonstratum to prove that this is equal. No, you just know it's been shown, it's been proven by experience. Okay, there is some things that are established that when your data is like this, you do this. When it's like this, you do this. So many decisions will be taken that way. But of course, we are humans, we are not robots. You should remain open-minded, flexible to try other things. Okay. Depending on the data you have, I've tried at times some analysis I've never done before. Depending on the data you have, it even gives better results than what is traditionally done. Okay. Of course, as a researcher and as somebody who has to background in epidemiology, I can explain that maybe in the background this happened and this happened, that has made my results more robust. But for a starter, you just have the basic knowledge, okay, that when it's like this, I do this. We're not going to practice with a particular software, SPSS or whatever. But all what I'm going to tell you is very generic, and you'll be able to apply it in the different packages or softwares that you have. Yeah. All right, we're going to move on. First thing you should know about statistical testing is the kind of variables you're dealing with. If you don't know your variables, you may not know which type of test to use. It's not one size fits all. It really depends on what you have at hand to analyze. So there are two big categories of variables, okay? Numerical and categorical. Numerical is, as you hear them, numbers, okay? These are numbers, 1, 2, 3. They're expressed quantitatively as numbers. And in numerical, you still have subgroups, continuous and discrete. Continuous simply means it's on a continuous scale and it can take all kinds of values. Like imagine between 1 and 2, you have 1.1, 1.125, 1.2, 1.3, 1.777, 8, 9, 10, 1. So it's continuous. It can take an infinite number of values, including decimal places. It can take any of that. It's on a continuous scale with no interruption between the numbers. And on this one, you have a discrete data. It simply means they are definite numbers. They are definite, okay, definite, how can I say, counts, if I can put it that way. For example, you cannot have 1.5 human beings. If you're in a classroom, how many people are in this classroom? You cannot say you have 71.2 people in this class. It's not possible, okay? Because human beings, for example, are discrete. It's 1, it's 2, it's 3, it's 4. It's not continuous. So we should bear that in mind because it's going to define sometimes what you have to use as tests. Continuous data can also be normally distributed or not normally distributed. Okay, we're going to see the implications later on. Normally distributed simply means, okay, the mean is equal to the median is equal to the mode. That's what it means, to really put it very plain. It means the distribution is not biased to one side or the other. It's a very uniform and, in quote, normal bell-shaped distribution. There are tests to do that. I'm not asking you to plot your graph and see. There are tests that you can check if your data is normal or not normal, but it's important before you analyze continual numerical variables that you know, is it normal or is it not normal? Skewed means it's not normal, okay? The mean is different from the median, is different from the mode. And there are tests to do that. It's important you define this before you rush into doing tests. You have categorical variables as well. Categorical variables are not numbers per se, but they are more qualitative. For example, in this classroom, there are how many males and females? Okay. You cannot quantify male, you cannot quantify being a female. They are qualitative things, but they enable you describe what you have at hand. Okay. So you can express them as proportions. 50% of the classroom is males, 50% of the classroom is females, and so on and so forth. Categorical variables also have subcategories known as nominal or ordinal. Nominal means no order. What is your sex, male or female? It's not as if one is first, one is second. In which region do you live in Cameroon? I live in Northwest, I live in Southwest, I live in Adamawa. There's no order. Okay, ordinal categorical variables refer to an order. When you say 1 or you say stage this is equal to, I mean, the value of one category is different from the other. Like a cancer stage, for example. When you say you have cancer stage 1, cancer stage 2, there are different categories, but you understand that stage 2 is more critical or is more serious than stage 1. All right. Kidney disease, there are different stages. Terminal, stage 1, stage 2, and so on and so forth. You understand when you say stage 3, that is different from stage 1. It's not just about a different category, but there's an order in it. The higher number means a more serious degree of damage or whatever. So those are ordinal. Order. Ordinal comes from the word order. The categories exist, but they are placed in a given order. Okay. So number of subgroups and frequency within each subgroup are key to determining which test to use. What do I mean by this? If it's about a variable like gender or sex, I prefer sex because gender is a big word. It's biological sex. You can have only 2 of them. Okay. Don't get me on the debate of no, this and that. I'm talking of whatever you're debating about is gender. But when it comes to sex, biologically, you have only 2 of them. okay, male or female. So those are the number of subgroups. In the categorical variable, gender or sex, biological sex, you have male, you have female. So there are two subgroups. It is different from a categorical variable like level of education, where you have primary, secondary, higher education. That's already 3 and more groups. You use different tests depending on the number of subgroups in that variable. Okay. And then the frequency within each subgroup. If in a classroom I have 50 people, 30 are males, 20 are females, it's a test that it's a particular test I'm going to use. If the frequency is different, let's say 4 are males and 46 are females, it's a different test I'm going to use. And we're going to explain to you why ahead of you when we go ahead. So the number of categories or number of subclasses in that variable and the frequency, number of counts within each category condition which test you will use. So these are all checks that you do before you start. Don't just rush into put my data here, enter in Excel, enter in SPSS, click here, click here, click here, and then analyze. No. These are some things you must do beforehand in your analysis plan before you actually launch into which technique to use. All right. Well, this is a summary, a summary of the variables that we have. You have variables are either numerical or categorical. In the numerical, you have continuous. Measurements can take any value, like height, like weight. It can be anything. 2.777 kilograms. It can be anything, but discrete, like I said, I took the example of human beings. You cannot have 0.5 human being. Discrete, the accounts, it's something that it has discrete values, and it can take a definite number of values. Nothing, it cannot just be infinite like continuous. Okay, and then you have categorical variables, can be ordinal, in which is an order, like kidney disease, like stage of cancer, or nominal, they're just categories, male, female. Okay, 𝐒𝐜𝐴, BMRC, if you talk about residents, you don't, there's no order, they are just nominal, no meaningful order. All right. Before you analyze, so before you analyze, you should know what you want to do. Are you going in for just descriptive statistics? Descriptive means you just take one variable and describe it, like the mean of this variable, age. The mean of the age was this. The median of the age was this. I have 100 people, their mean age is this, their median age is this. Or do you want to do inferential statistics? Inferential means you're already doing comparisons. You're already trying to look for associations. Okay. Instead, maybe you say, I don't just want to describe that the mean age of people in this classroom is this. I want to see the age, compare the ages of males and females. That's already inferential. Okay, the mean age of males compared to the mean age of females, and then you do a test, and then you have a p-value and all of those things. Okay, there's no wrong, there's no right. The person that descriptive is not wrong. It depends on what you want to show. I may just want to show that in this population, the mean height is this. Okay, when you look at WHO curves, for example, I suppose all of us maybe are into the medical field, the growth curve of WHO. Okay, that at this age, the child should have the mean weight of the child, you know, at 5 weeks, at 10 weeks, the child should weigh 2 kilograms, 5 kilograms, I don't know. Okay, these are descriptive data and they're very important. They're not less useful than somebody who run a big model or regression, whatever. At times, just descriptive data is very important. So WHO has done studies on thousands of children and has found that when children are 5 years old, their mean weight is this. That's just descriptive. They've not compared it to anybody. That in this population, in this country, for example, at this age, the mean age is this, standard deviation, this and this. That's descriptive. So you have to know beforehand what you want to do. If you want to be inferential, I want to compare the weights of children in Cameroon and in Ghana. That's inferential. You should really tell you what kind of tests you're going to do or which direction you take in your analysis. Good. Other checks you should do before you analyze. For numerical variable, like I said earlier, you must check whether it is normal or not normal. Check the normality of the distribution. And as I said, there are tests for that in your softwares. You don't need to do it by hand. There's the Shapiro-Wilk test, there's Kogomiros-Smirnov test. Those are the most common ones. There are other ones, okay? Which when you have a continuous variable, You select that variable in your software, whatever it is, click that okay, normality test, and it will tell you. And the test, maybe I should also tell you how to interpret the test. The test investigates whether that variable that you're presenting is significantly different from a normal distribution. So if it says p-value above 0.05, like a non-significant p-value, it means that that distribution is not that different from normal distribution. You can assume that it's normal. It is not different from the ideal normal distribution. But if the p-value is less than 0.05, that means a significant difference. It means that variable that you have, maybe age, its distribution is very, very different from the normal distribution. So don't treat it as if it is normal. So the test for normality actually looks for differences with the normal vis-a-vis the normal distribution. And if it is significant, then it is not normal. It's very different from normal. So you treat it as not normal. And it's going to influence the choice of your test because normal distributions employ parametric tests. We're going to see ahead what it means. And non-normal distribution use non-parametric tests. You could be looking for the same comparison between this and this, but just because something is normal and something is not normal, it could make a whole difference in the test you will use. Excuse me, and it could give you different results altogether. So you should be keen on what you want to do. The checks that you should do for categorical variables, and particularly when you have just two things to compare, okay? Like I want to find a situation between I don't know, living in Yaoundé and being a male. So you're comparing residence and sex, okay? You should make sure the test you will use depends on the number of counts in the cells. We are going to explain as we go ahead, okay? Like I said earlier, if in a class you have a class of 50, you have 4 males and 46 females. Just the fact that there are less than 5 in one category, that's males are less than 5, there are 4. It's a different test you're going to use than if it was maybe 10 males and 40 females. So you should check some of those things, like what is the frequency in the different categories? And if it's below 5, there are certain tests that you should do to attain certain precision. If you use the other tests, they are not precise enough to discriminate when the counts are different and less than 5. So that also condition the kind of test you do. So those are all small checks you should do with your data. I mean, these are real things. These are hands-on things. You can even open your data right now and check that, okay, check normality, categorical variables, I have the categorical variable of sex, I have the categorical variable of level of education, I have the categorical variable of this. I should make sure that in each of the subgroups, I have at least 5 and above. Or if in a particular subgroup I have less than 5, you note that down. It will determine which test you should use when you're working on that variable. All right. Now let's get a bit more practical. Okay. My slide is delaying to change. Okay, it's gone. Good. Let's get a bit more practical. Now you have one continuous variable. Okay. You do what they call a one sample t-test if that's parametric. For example, you went to a village and collected the height of children age, I don't know, 0 to 5. You measured their height with a meter. Child A is, I don't know, 1 meter. Child B is 96 centimeters. Child C is 0.98 meter. Child D, you measure their height and you have a whole set of data from these people. You have nothing else to compare. You do not measure it. You don't measure the data in the height in one village and then another village. You just measure in one village. And let's say you measure only among males. You take only boys. You measure the height only of boys of a given age. Okay. How can you do a one sample t-test? You will just need the mean height of another distribution. You don't need the entire distribution. You don't need another data set with 1,000 children. But you can just scan through literature and say, okay, in this other village, the mean height of children age 5 was this. And then you can compare the mean of your own continuous variable with the mean for another population without necessarily having the whole distribution of the other population. Okay. So usually you require just one normally distributed variable. I can do a one sample t-test. You don't need much data for this. Okay. Significance, of course, if you set it as at 5%, it will be that. If p is less than 0.05, it's significant. So the good example I took here is comparing the mean height of children in a village with a known mean height of children from national studies. So you know that in Cameroon, a child at 5 years maybe has a height of 1.2 meters. I'm just taking an example. Okay, that is known, it's published. You then go to a village, you measure the height of 1,000 children at the age of 5 years. So you have child 1, child 2, child 3, up to child 1,000 with their heights. You can do a one sample t-test to compare whether the mean height of my population, is it different or it's close, similar to the mean of the national population. Okay, at times you need that kind of information to make a decision clinically or therapeutically and so on. So it's one kind of test. You need just one variable for it, a continuous variable, normally distributed. So this is pretty simple. There's now a case where you can also have two continuous variables. How do you then handle that? When you have two continuous variables, there are many things you can do. And the simplest of them is a correlation. Okay, I say simplest of them because correlation is simply a linear association. It's a linear relationship between variable A and variable B. As variable A is increasing, is B also increasing or decreasing? That's pretty simple. It's a linear relationship. It's a linear relationship. And like I said, you must always check whether data is normal or non-normal. If it is normal, you use a parametric test called the Pearson correlation. And if it is non-normal, skewed, you use a non-parametric test known as the Spearman correlation. And generally, it will give you a result between -1 and 1. It cannot give you 1 point something or -1 point something. It's always between -1 and 1. And it is interpreted in different ways, okay? The sign, negative or positive, tells you the direction of association. Positive association means I go in the same direction, okay? As I increase, as A increases, B also increases. That's positive. Negative means they're in opposite directions. Okay. As A increases, B decreases. That's what the sign tells you. And then the number tells you the strength of association. 0, which is in the middle, means no association. And the more it goes away from 0, either to 1 or to -1, that's the increasing degree of association. Okay. I put an example here comparing height and school average. Those are two continuous variables, right? And you want to see that is it that as height increases, average also increases. Maybe people who are very tall have better school results. Okay, that could be a correlation analysis. And you could either find it to be positive, to be negative, or even 0, like there's no relationship at all. You can be tall and very stupid, in quotes. All right. So this is a pictorial or graphical representation of correlation. You can see here, this is a positive correlation. This is 1. Okay, when this one increases by 2, this other one increases by 2. So if you plot here, it'll be 2, 2. If you plot here, it'll be 4, 4. You plot here, it'll be 6, 6. So it means as this one increases by 1, this one increases by 1, this one increases by 1, and perfect correlation. This is still a positive correlation because the trend is positive. The trend is a line with a positive slope. Okay, but it's not perfect. It's not aligned, but it's about 0.8 or so, which is still quite interesting. It's a strong correlation positively. This I put there 0 simply because if you want to ask a software, even Excel or whatever software, to draw a line that summarizes these points, it will be like a horizontal line. Okay, so if you make like this, it will cancel out and you have a horizontal line. And a horizontal line means the two have no relationship. When it's not a horizontal, what does it mean? Down the x-axis. When I'm at 2, this man is at 4, for example. When I'm at 6, he will still be at 4. When I'm at 10, he will still be at 4. So I'm increasing on the x-axis, but nothing is changing on the y-axis. It means they're not related at all. Not at all. They have no connection together. Okay, they're independent. That's the term they use in statistics. This one here shows a negative correlation. As this one is increasing, this one is decreasing. All right, like the demand curve. For those who remember, this one leads from 0 to 2. This one rather leads from 10 to about what, 8. Okay, if you want to see the points are plotted here. So as I'm increasing this way, I'm decreasing downwards. This is a more negative correlation, just like up, you see a trend of a line going downwards. And this is a strong correlation with an outlier. So all the points will rarely align like this on a graph. You always have more of these some scattered points. So at times you have an outlier, somebody who's really off topic somewhere here. Okay, and at times you have to look into that. Why is this person outlier? Maybe data was not well collected. Maybe he did not meet the inclusion criteria, therefore his data is very funny. So in research, at times you look at this guy to find out, was there a mistake or it's just a random occurrence? Now, two continuous variables, you can also do something else besides correlation. Okay, you can compare means and medians of continuous variables. Correlation just tells you a direct association, like linear. As I increase, you increase, as I decrease, you decrease. That's all it tells you. Okay, but here we're getting a bit deeper. You may want to compare the means of two continuous variables. Okay, and that will condition how you go about it. Sorry, I have to check. Okay, that will condition how you go about testing them. I took an example here, visual acuity, left versus right eye. Okay. This simply means when you go and see the ophthalmologist, they will do visual acuity and give you a number. It's a continuous number. It will be, you have a visual acuity of 5, you have a visual acuity of 6 on your left eye, and so on. So you may want to compare the two. There are two different variables which you want to compare their means or their medians. We'll see which one corresponds to what at the end. It could also be that you have the same continuous variable, but you want to compare them across categories. For example, I spoke of height earlier. I've gone to a village, I've taken children of 5 years old, I've measured their height, all of them, and I have a mean height for all these children, which I can compare with the mean height of the national data. That's a one sample t-test. Now, within those children that are tested or that are measured their height, I have males, I have females. I can decide I want to compare the height of males and the height of females. Okay, though I have one continuous variable, I can split it in two categories, so that I can have two distributions. I have the distribution of heights for males and distribution of heights for females, and I can compare them as two continuous variables. It is one variable, but once I split it by category, it becomes like two different variables. Okay, height of males and height of females. All right, so let me go to the nitty-gritties now. You must always check if your data is normally distributed. If it's normally distributed, you use a parametric test.
Let me jump in question, Joseph, just for clarity's sake.
Yes, please.
Should we always divide our data by male and female and make comparison, or should there be something that should drive that process? Because I always see it in theses that I read, in some papers that I read.
Yeah.
Is it good practice, actually?
It is good practice because more and more principles of fairness, fair data, and so on, sharing data and how it should be presented, tell you that you should present disaggregated data. Okay, and male, female, sex in general is an important variable because of what they call biological plausibility. When doing health research, most of the times, data may vary between males and females, like diabetes, like hypertension, and so on. We all know that there are risk factors. Just being a male is a cardiovascular risk factor compared to being a female. So I expect maybe a male population to have slightly higher blood pressure values than females. And when everything is mixed together, it's difficult to disentangle that. So it's good practice. It's actually encouraged that you present your data in the most disaggregated way possible. That means you may have collected data from 10 regions among males and females. Some of them were secondary school, some of them were high school, some of them were university, and so on. As much as possible, presenting a table that shows among males and females, this was it. Okay, by level of education, this was it. By region, this was it. As much as possible. Of course, you cannot present all your data. It's impossible. Usually, you have very huge data sets.
Good.
But
so
as much as possible, present disaggregated data. Yeah.
I'll jump into that because
yes, please.
That the tendency, therefore, will be to want to disintegrate the data by different category. And what do you think? You've mentioned biological plausibility, which I think it's very important. Of course, as we know in epidemiology and causality.
Yeah.
And I think where the point I was trying to hit is that why that is important, it also depends on the question that that researcher wants to answer. And
Definitely.
you mentioned diabetes, where we know, and hypertension, where we know exactly that there's a male to female gradient. In diabetes, in hypertension, in diabetes, there's a race gradient, for example, as we know that we of African descent are more at risk, most likely to have hypertension and other of these, chronic diseases and even cancers, as we know, breast cancers today, prostate cancer, and all of that. So that makes sense to want to show that biological difference, right?
Yes, definitely. Yeah, thanks for that, Dr. Kate. I think, as I said, biological plausibility really cuts across many topics, in medical research, and most of the times you need that. But don't be robotic. Remember, in my first slide, I said it's also about you being open-minded and flexible. At times, you don't really need it.
Exactly.
At times, you don't really need it, and don't just be robotic. Okay, but most of the times, when it comes to health research and health outcomes, usually sex has an influence, and it will be good to present it that way. Right. So be flexible, read your data. Okay, that's why I said it really comes with practice. I can't give you a playbook. You read your data, you feel your data, you put yourself in the shoe of the reader. Like, what will I want to read? What will I want to discover, to put out there? Okay, from this data. It's important. As a professional, you grow better at it the more you work with data sets, but you have to start somewhere. All right. So in this case, when you're comparing two continuous variables, if it is normally distributed, again, you must do the test. Okay, you compare means, and that's a t-test. A two-sample t-test this time around. And if it's not normally distributed, you compare medians. Okay, and that's a non-parametric test called Mann-Whitney-U. Some softwares will call it the Wilcoxon rank sum test. Okay, it's the same thing. Not to be confused with the paired test. Wilcoxon paired test is a different thing, but rank sum is the same as Mann-Whitney-U. And of course, if p-value is less than 0.05, it means the difference in means, if continuous, if normal, or in medians, if not normal, is significant. And you can conclude based on that. So when you have two paired continuous variables, what's the meaning of paired variables? Paired variables are usually variables taken from the same individuals. Okay, like the example I put right down here, systolic blood pressure before and after taking a drug, paired by patient ID. Like the same person will measure your blood pressure, okay, and you have a certain value, I don't know, 140 or 90, and then they're testing a new drug, they give you that drug. After a while, they test again, they measure your blood pressure, systolic, and it's maybe instead of 140, it's gone down to 120, something like that. So to analyze that, we really say some degree of finesse and to really have precise outcomes, it would be judicious to pair that your before and after value. Don't just collect for all patients before and for all patients after, and then you compare and so on. That will give you some results, okay? But to really add some finesse, when you pair, it can really say that it is that intervention that made that change in you. But when you just take a whole distribution of before, a whole distribution of after, anything could have happened to anybody, okay? And that maybe you see a small difference. It doesn't explain it that deep. Paired is a bit more fine, all right? So this is a good example. The same patient, you measure BP, you do an intervention, you measure BP on the same patient, you can do a paired analysis, all right? So it follows the same logic as non-paired tests. You can compare means, compare medians, and so on. But in this case now, the software, the calculation takes into account the fact that value this on before and value this on after correspond to the same person. And it enters in the algorithm before they give you a response, okay? And when the data is normally distributed, you use what they call the parametric, the t-test, the paired t-test. It's the same t-test as before, but you input that variable, that this variable is pairing, like patient ID, for example, is a pairing. So patient ID 1, there will be a column for BP before, a column for BP after, and then when you say pair by ID, you will know that for patient ID 1, whatever is patient ID 1, you know, before and the before and after, which corresponds to patient ID 1, is the same person. Therefore, analyze it that way, and it's going to do that in the background. So it's a pair t-test for the parametric version and the Wilcoxon pair test for a non-parametric version. All right. Continuous variables compared across 3 or more groups. So far I've been saying just 2 continuous variables, okay? Maybe males and females, maybe in region A versus region B, okay? Maybe before intervention, after intervention, but you can have much more. You can have many more categories, okay? I can want to compare, look at the last line here. I want to compare SAN scores in 5 medical schools, for example. Now we know that everybody writes the same SAN. I want to say, okay, between Bamenda and Boya and Yaoundé and UDM and all, I want to compare the scores. I can't use a t-test here or a Wilcoxon ransom test, okay, because those work only for 2 categories at most. Those work for 2 categories. When I have many more categories, I need a different test. So you see why it's important that before you analyze, understand what your variables are. If you are dealing with sex, male, female, fine. You can use the one that just handles 2 categories. But if you have a variable that has so many categories, region of residence, let's say you did an online survey. Some people answer from the north, some people answer from the south, some people answer from littoral, some people answer from anywhere. You can't just say, okay, to see the difference across regions, okay, you come and do a t-test or I don't know, Man-Whitney U test when there are about 10 regions. You will not have accurate result. In fact, the software will tell you error, that this test only works for 2 categories. Okay. So when it's 3 or more groups, you go to what they call the analysis of variance. All right. Analysis of variance now is able to take into account the several groups and compute those differences in a certain way to let you know if there are really differences across these categories or not. So coming back to my example of SAN scores, usually they are in percentage, right? You can have 50%, 70%, and so on. So one school can have a mean percentage. They take if they have 100 students, they take the scores of the 100 students and divide by 100 to have a mean SAN score for that school. Okay, which can be compared with other schools. If it is normally distributed, of course, you can compare the mean. If the normally distributed is a median. And so when you have a parametric or normally distributed and you compare the mean, you use what you call the one-way ANOVA. The one-way ANOVA compare not just the mean, but also the variance, like how does the data vary across these different groups? Are there overlaps in the variance? Okay. It would check not just that point value of mean, it will also look a bit at the distribution. How does it vary? Do they overlap? Does one category, one school really, is it very close to the next? And so on and so forth. When it's just 2, it's easy. When it's just 2, it's easy. When there are many more now, you have to interact if it's school A, B, C, D, E. You have to interact different between A and B, A and C, A and D, B and C, B and D, B and E. You have to take into account all of those. So you can't just use the normal t-test or whatever. And that is what the one-way ANOVA will do for you. If it's non-parametric, the Kruskal-Wallis will do that for you. So when you now see all these big terms, Kruskal-Wallis, Man-Whitney U, you should now know what they correspond to in papers or in publications or even in textbooks when you're reading. This is what they're used for. These are rules of thumb. Just know that it's like that. All right. So another important thing here is post hoc. If you find a significant difference, if maybe you compare the SAN scores across 5 medical schools, assuming, for example, that they are not normally distributed. Exam scores are not usually normally distributed. So they are not normally distributed. So use non-parametric tests, Kruskal-Wallis, and you will have, you find a p-value less than 0.05. It means across these 5 schools, there are differences. There's a difference somewhere between the scores of some schools. But it doesn't tell you that it is school A that's different from school B. or it is school C that's different from school D. It doesn't. When you're doing a post hoc test, softwares also do that, SPSS, R, and whatever you use, they have that. After, if you find a significant difference, you know, you can now go and do a post hoc test, and it will tell you exactly where that difference is. It will show that this p-value is significant lie is simply because the median for school A was 25 and the median for school E was 75. So that's where the big difference is coming from. And maybe the others were pretty close to themselves, 65, 62, and so on, not so different. But it shows you clearly that the difference is between this and this. And at times it's interesting to know that don't just say across the 5 schools there was significant difference in scores. That's information-based, incomplete. You can do better. So when you do a post hoc test, you actually tell the reader that that difference came from the fact that, okay, school A and school C were very far apart, and this difference was significant. However, between school C, D, and E, there was no bit. I mean, you can go that detail when you do a post hoc test. Good. Man, this is not finishing. Anyway, we're almost done. Categorical variables. So far, I've been continuous, right? Categorical variables now, you don't have to check for normality. It's not continuous data, it's not numerical data. So here you can just go direct. What do you check? At the beginning, I said after normality, you check what? The number of counts in each category, right? You should make sure you don't have less than 5. And I'm going to explain as we go ahead. We're going to see the tabulation and explain what it means. If in a class you have 2 males and 48 females, you cannot use a chi-square test. Okay, chi-square test is good when you have more than 5 in each subgroup. Else, it will give you a result. I'm not saying it will not work, but that result will not be very precise. It has been shown that chi-square test works best, okay, when you examine your subcategories in your variable and you say, okay, it's 5 and above for all of them. Then you can use a chi-square test. That is what you should use. The number of categories don't matter. Okay, it can be the 10 regions of Cameroon, it can be the 54 countries of Africa, it can be whatever, as long as in those categories you have 5 and above, okay, counts for that variable. What I mean by count is like in a classroom, you want to analyze by sex. You should make sure that in each sex, male, female, you have at least 5 people. If you have less than 5 just in one of the categories, chi-square test will not work that well. Okay, but number of categories themselves don't matter. It can work well. It can work well no matter number of categories that you have. All right. And when you run the chi-square test, you have what they call a chi-square statistic. It's a number, okay, which simply shows the association. If it is very high, it means it's a strong association. If you have a chi-square value of 5 and you have a chi-square value of 200, of course, the one of 200 shows a stronger association than the case of 5. So that number at times is not reported, but it tells you the analyst when you're analyzing the association is really strong. Some people put it more and more, people put in publication, but usually just see the p-value. There was significant association between sex and I don't know, sex and having yellow hair. Okay, p-value this, they just put like that. But at times the chi-square will tell you how strong that was. So it's a good practice also to at times report it when you can. Some journals even expect it right now. Some journal are publishing a journal recently, and at the last stage when they were doing the editing, it was already accepted. And they said, please give us the chi-square statistic here before the p-value. So more and more they're going to ask for it. Oh, did I get lost at some point?
Yes, but
it's like I got lost at some point.
Yes, you need to reshare your slide.
Let me reshare, and you will tell me where I got lost.
You were talking about categorical.
Sorry?
You were talking about.
Okay, I'll reshare my screen.
The one before this one?
I was before this one.
Yes, you were here.
I was here.
Yeah.
And so I was explaining basically that, let me hide all these things out. clouding my screen. Yeah, I was saying basically here that the chi-square test can work on any number of categories. I don't know if you got that. I said it can work no matter the number of subgroups. It can be that I'm comparing the number of males, the number of this by sex. I'm comparing the 10 regions of Cameroon, or in the 54 countries of Africa, or in, I don't know, I can have 1,000 categories. It's going to work. The only emphasis is that in each of the categories, I should have at least 5 counts. The simple example that I took earlier was that if in a classroom of 50, I have 2 males and 48 females, I cannot use a chi-square test. It doesn't perform well when a category has only less than 5 counts, like 2. So when I'm looking at my data before analysis, I check in each subcategory. Maybe I'm classifying my participants by region of residence. I should make sure that of all the 10 regions, I should have counts of at least 5 in the category that I want. Like if I want to take number of females, I want to do by sex and by region of residence. I should make sure that I have at least, in each region, I have at least 5 males and 5 females in each region before I can use the chi-square test. If one of those boxes, as I call them, has less than 5, there'll be a problem. The chi-square test will work, it will give you results, but it will not be very precise. Okay. And I said the higher the chi-square statistic is, the stronger the association. The chi-square statistic is simply when you do the chi-square test, it tells you the chi-square statistic is this number. It's a number, okay, don't overthink it. But the higher it is, the stronger the association between those two categorical variables. If I have a chi-square statistic of 500, for example, and I have another one of 10, of course, it means 500 means the association is more stronger than the one of 10. It's just interpreted that way, just logically. The higher it is, the stronger the association. Now, let's see what is done in the chi-square test properly. Okay. I took my time to explain this chi-square test in particular because many people find it difficult to interpret it, and it determines even how you are going to state it in your paper, that there was an association between this and this. It helps you to understand what you're saying. At times we just read it and we're just happy that p-value was less than 0.05, but we don't even know what is going on. So let me illustrate the chi-square test to you. I want to see if smoking is associated with lung cancer. Okay, that's a question. So I have data from people who smoke and don't smoke, and those same people have information if they have cancer or not cancer. What I do know is that the prevalence of cancer is 10%. So of the 200 people that are recruited, I know if I just say the variable cancer, 20 out of 200 have cancer. That's 10% prevalence, right? What I expected is that among smokers and non-smokers, the prevalence should be 10%. Like if there's no influence whatsoever, if I know the overall prevalence of cancer in my population of 200 is 10%. When I categorize it into males, females, or into smoking or not smoking, the smoking side should also have 10%, and the non-smoking side should also have 10%. That's what they call expected. So out of 100, this is smoking, okay? Smoking, yes, and smoking, no. So out of 100 who smoke, and out of 100 who do not smoke, I expect the prevalence, okay, to be the same, to be 10%. So 10 out of 100 who smoke should have lung cancer. 10 out of 100 who don't smoke should also have lung cancer. So that at the end, overall, 20 on 200 is 10% overall prevalence. So that's expected in the ideal world. So, but in the real observed data, what you found is that among those who smoke, 15 have cancer. And 85 don't have, so 15 out of 100 have cancer. And among those who don't smoke, 5 out of 100 have cancer, to give you that overall prevalence of 20 on 200, which is 10%. So this is what you observe. But from the overall prevalence of 20%, of 10%, sorry, I expect this, that among those who smoke, prevalence will be 10. Among those who don't smoke, prevalence will be 10. What the chi-square does is it compares your observed with the expected. So it compares A with A star. So it compares this A here with this A star. That under normal circumstances, if the prevalence was really uniformly distributed across all categories, I should have had 10 here. But in reality, those who smoke, I have a bit more who have cancer. So it compares this and this, compares B and B star, it compares C and C star, it compares D and D star. And so the test works best when each of these cells here, okay, are 5 and above. If here, for example, was less than 5, 4 or 2 or whatever, I should have used the Fisher test, Fisher exact test. When there's a value below 5, you should use, in the table here, when it's a value below 5, you should use the Fisher exact test to have more precise information. Now, you must not cram this, but to give you a better view, when they say chi-square test, this is what it means. This is what happens in the background. You should be aware of it. Chi-square test simply says, okay, in the ideal world, this condition is present in 10% of people. So whether I have 10 categories, in those 10 categories, 10% of those people in each category should have that condition. That's what is expected. But if those categories influence significantly the outcome that I have as 10%, of course, those who are exposed to that, in the observed data, they will have more of that outcome than those who are not exposed in the other categories. And so the chi-square test examines that probability of, does the exposure to this thing actually change significantly the prevalence or the outcome of this thing compared to what I expected? Some changes may just be by chance. And so your p-value will be non-significant. Okay. I could observe, for example, 11 here and 89 here. Okay. I could observe, for example, 6 here and 94 here. Okay, so it will compute that difference. Is it just chance? Or actually it means that categorization into smoking and non-smoking has something to do with having cancer or not? So that's how it works. Just have it at the back of your mind, that's how it works. And the software just gives you the response. And the p-value will mean there's a difference and it is significant or not significant. All right. I think that was the last test that I was looking at. So it's a summary, okay? I hope you can all see this table, because this will summarize everything I've been saying so far. And to be candid with you, I had a table like this written out, pasted somewhere when I was doing my PhD, when I was really growing in research, okay? Because it's not intuitive. Now, for me, it's almost normal, but I had to grow into it. So whenever I went to the field, collected data, I will open that drawer and check where I pasted this. I said, okay, which kind of data do I have? I have 2 continuous data. Okay. So I can just check correlation. If I'm to check correlation, what can it be? If it is parametric, it's Pearson. If it's non-parametric, it's Spearman, and so on and so forth. So this table summarizes all what I've been saying so far. And I advise you can take this slide, print it out. Okay. You can take this slide, print it out, and just use it as a reference. I did that until now. I've grown into it and it's almost normal. Okay, but at times you are still very confused. You should know what's adequate for what. When you have one continuous, which is normal, and you have 2 categories, like you have the height of children in 2 countries, the categories are countries. If it is normally distributed, okay, you compare the means, that's a t-test. If it is not normally distributed, you compare medians, that is a Mann-Whitney test, or what I call the Wilcoxon rank sum test. Okay, these are examples to make it a bit more real to you. If I have one continuous variable normally distributed and I have 3 categories or more, okay, like the mean height of children or 5-year-old children in 3 countries, that's more than 2 categories. I'll use ANOVA if it's parametric. If it's non-parametric, I will use Kruskal-Wallis. Okay, like GPA of EM1 students in 4 schools. Okay, GPA at times may not be parametric, may not be normally distributed, so I use non-parametric. And since there are 4 schools, that's more than 2 categories. Okay, I will need to use a Kruskal-Wallis. If I have 2 categorical variables, no matter the number of categories, it could be just 2 categories like sex, male, female. or it could be 1,000 categories, or it could be 10 categories like regions of Cameroon. It could be 54 categories like countries in Africa. No matter the number, I put N here to say no matter the number of categories, okay, and you have two categorical variables, you can use a chi-square test to see association between those variables. And it compares the observed versus expected, as we saw in the previous slide. All right. And I emphasize here again, you have to double check that the counts in each box or in each cell are 5 and above, else your test may not be very precise. More and more softwares automate these things. So when it does a calculation, it tells you already error message that you have a cell with less than 5 and so on and so forth. Some softwares do that already, but it's good practice just to check to be sure. All right, I should be rounding up. To choose the right statistical test, okay, I wrote this thing with having in mind that, okay, this is you and your data is in front of you. What do you do? This is you, you have your data in your computer. What do I do? I want to analyze, what do I do? So this is like a checklist. First thing I do, what kind of variable am I dealing with? Mind you, each variable will have its test. You cannot take a whole data set of, I don't know, 20 variables and just you are going to run one big, mighty chi-square test and it's going to work, or one big, mighty t-test on the 20 variables and it's going to work. No. You go row, column by column, variable this, which one variable is it? If I'm to compare to variable this, which test am I going to use based on the different characteristics? Is it normal? Is it categorical? Is it? So always ask yourself, what kind of variable am I having? The second thing I should do is understand the test output and interpretation of the p-value. Before you say, let me run a t-test, okay, it's going to tell you p is equals to 0.004. And you're happy because I don't know, MD students in this always look for p-value that's below 0.05. Even they don't know what it means. What does it mean? Before you run the test, you're like, if this test actually comes out, what does it mean? Something as simple as a normality test. You run the normality test, it's easy. You enter your software, you select your variable, I don't know, age or whatever it is, click normality test, 𝐒𝐿, or whatever, enter. You run the test and tell you p-value equal to 0.00001. And you're happy that, yeah, it simply means the data is not normally distributed. It is significantly different from the normal distribution. So before you run a test, double check. Go to the internet, go to textbooks if needed, but understand that as I'm running this test, I should not be happy of a value that will come out. I should know what it implies. Because at times, the result of one test will lead you to doing another test. So if you're just doing things blindly and robotically, you will miss on a lot. I spoke about Kruskal-Wallis or ANOVA when you have more than 2 categories and you have to compare a continuous variable across more than 2 categories. Once you have a p-value which is significant, you have to do a post hoc test to see among these many categories, where is that difference coming from? If you're just happy that the P is like this and you stop there, you are going to lose a lot. So understand what that test you want to do, the output and interpretation of the p-value, and always verify your assumptions. Is it normal? Is it not normal? Are the number of items for the chi-square test more than 5, as I said? If it's less than 5, the Fisher test should be more appropriate, and so on and so forth. Okay. Generally, the larger your sample size, the easier it is that you fulfill assumptions. If you have a sample size of 2,000, it's very unlikely that you have a cell with less than 5. Okay, usually those assumptions are met easily. Or if you have a sample size of 1 million people and you are looking at age or at weight, it's very likely that you'll be normally distributed. Okay, because the more data you have for some kind of variables, the more likely you have a normal distribution. You can use all the parametric tests that you want to use, and so on and so forth. I didn't enter into regression models here. Okay, logistic regression, linear regression, and so on. That's a separate chapter. If you understand these bases I'm teaching you now, even on your own, you can go. I learned the regression on Coursera. You can go on your own and read those things, and you understand because they build on top of this. They build on top of this. So focus on understanding these basics, and then when you grow to read other things a bit ahead, you understand better. So I said rules of thumb exist, but intuition remains important. And here I appreciate particularly Dr. Kate's intervention about sex. Don't just say they always put sex. Use your intuition. Okay, use your intuition. Rules of thumb say, okay, present it as male and female, but use your intuition also, like for this particular case, maybe this is better, maybe this is better. That's also part of data analysis. Don't be robotic. There are rules of thumbs, but think, feel your data, feel it, look into it, let it speak to you. That's why it's very important to have a good literature review of your subject matter. Don't just rush into copy paste, you know. We student even did this last year. Okay, this daughter also worked on diabetes last year. Let me go and enter the literature review. Just copy and paste without reading it. Knowing the literature will help your intuition that, oh, I read that in this case and this case and this case for this particular kind of outcome, sex is important. I read that for this particular kind of outcome, maybe country of origin plays a role. I read that residents, rural or urban, can affect this kind of output, and it will give you an intuition on what to analyze and what to present. So, dear listeners, when they tell you, even in articles, that the first part is background and literature review, it's not just to put label on you, it's to make sure that you have understood the topic, you have understood what you're looking for, what you want to analyze before you get into the numbers and statistics. Don't skip that part. All right. So these are very basic principles. Okay. Like I said earlier, but it gets more complex. You're going to run into models, you're going to run into regression, you're going to run into, all kinds of things. But you need to understand the basics first. And the more you do it, of course, the more you perfect. I am not a pro. I don't want to say I'm a pro, but I'm surely way ahead of 1 year or 2 years ago, because I keep doing it. And the more you do it, the more you realize, this approach is better. There are even there's data that I've published. You can find out in published job, but when I look back at the data now, I say, oh, I would have analyzed this thing differently if I knew better. But well, it's already out there. So as you grow, you also mature in the way you approach data. Okay, and your results, the outcomes become more fine, more refined, and more interpretable, more reusable based on how you have grown and matured in the topic. Yeah, I think this should have been my last slide. And I'm going to leave the floor open for questions. I'm just checking my watch now. Sorry, I went like 10 minutes overboard. Yeah. Over to you, moderator.
Yes, 10 minutes overboard will not be an issue based on the richness of what we have heard so far, giving us the basic outline for us to conduct good statistical analysis for our research. Thank you so much, Joseph. So you can stop sharing so we can have a full gallery view and
all right,
open it up for questions. Really, if you have a question, you can just raise up your hand or just unmute yourself and go for it. If two people are speaking, then I would jump in to moderate. There is a question coming from the chat section. Is there a limit? It's a question from Dr. I guess this is Dr. 𝒆𝒔𝒄𝒉, if I'm not mistaken, who probably should be joining from Douala, Cameroon. That is there a limit to the number of statistic tests you can do in one analysis? What's the best practice regarding this?
Okay. Should I say upfront, there's no limit? Data is open. You interact with the data. You interact with data freely. Usually what you even see published, know that they have tried to see the best fit to explain maybe the finding that they have. Don't feel like they just will enter like that. It came out, they just copied and pasted in their manuscript. Okay. At times you do it, you get it checked, you get it rechecked, and okay, if I add this other parameter, how does it behave? If I do this, how does it behave? And so on and so forth. So, stricto sensu, there's no limit, but at the end, it is good practice to limit yourself to what communicates, okay, some sense, to what communicates something relevant. because you can do anything with data. I can test anything on any data. I can test, I mean, what's the probability of somebody wearing a yellow shawl? You know, I'm saying anything. If I have the elements, the data, the information in my database. But how will it help if I put it out there on a whole page, showing how, you know, I tested this, I cross-referenced with this and this, and I found the probability of somebody leaving his house in the morning with a yellow shawl is this, p-value. Yes, you may have even done it correctly, but is it relevant? So when exploring data at your own level, in your own desk as a researcher, do all those things, pick out what is most relevant, and then you put it out there. It also speaks of your credibility. It's a bit like coding, okay? In coding, they usually say that the best coder is he who uses the least lines of code to do a particular task. When you're coding computer, I'm talking about computer coding. You can code a certain command in 50 lines. You will do the command quite all right. Somebody else will come and type 2 lines of code and do the same thing. And generally in the coding world, they will tell you the person who uses the least number of coding lines to do a certain task is a better coder. It's almost the same analogy in statistics and in research. The person who is able to report the most relevant things using the most synthetic approach without bothering us with a lot of crowd, you know, without overcrowding our view. You just go laser focus, pack. This is what I have. This test revealed this and this and this. It is relevant for this and this and this implications. It means this and this and this. We are happy. Now, if you find some very interesting other findings which you think should get out there, you can put in supplementary. Okay, you can publish a paper and then you have supplementary data, supplementary appendix. Okay, I found this interesting and it's analyzed in the supplementary. Maybe it's too bulky or not very in the flow of the logic of my paper to put it in a table here, but it's good for readers to be aware that my data also show this and this and this. You add your supplementary and you cite it in your work. Okay, by the way, you see, okay, furthermore, I found that this is related to this, as can be seen in the supplementary appendix 1. And it's also available on the website. The person can go and download it and check what extra thing your data was saying without necessarily losing the line of focus or the flow of your article. Yeah, so in theory, there's no limit. Do whatever you want to do, but report it in a way that really speaks of your expertise.
Yeah, and just really to coin all what you have said and to make it very didactic for comprehension's sake, Dr. Ashu, I would say your analysis or your research question should drive your analysis. First thing first, that's where you talk about that focus. And that is why today in very big studies, for example, they would want you to have a published protocol. Like, especially if you're in the case of a trial, we want to see a protocol, we want to see that being registered beforehand, so that at the end, when you're publishing, we are not just seeing things that you have tried to best fit, but you've tried to answer the question that was set out initially to do, Okay, and so that is important. Another thing you must consider, Dr. Siwe mentioned the fact that other things you find can go into supplementary. So that's very important. So as you do your analysis, your main, oh my God. As you do your analysis, your main research question and your analysis, first of all, should be focused around that. Your analysis should be focused around that main research questions. And subsequently, other things you find go into a supplementary presentation of your data. So that is key, because that will now avoid what cherry picking, because many people now do cherry picking. Oh, I've done this and I've done this association, it's not significant. Okay, let me try this other association. I try it's not significant. Then I try association is not significant. I try a fourth association is not significant. So set out, I'm really an advocate for having a research question upfront. Set out to answer that research question. If it doesn't answer that research question, then it probably, if the design was done well, it probably falls within what we call a negative research findings.
Research, yeah.
And they are also important in, in the body of knowledge creation for science. I mean, I have a couple of negative research findings studies that have been published, including trials which we did in Cameroon. So what I'm trying to advocate is that we should uphold a sense of scientific integrity, even as young researchers growing up, and not just want to cherry pick and at times manipulate data in order to show statistical significance.
To force a finding.
Yeah, to force something out of your data. So that is bad practice, and many people do that, and which is not good.
Yeah, just to reiterate on what you just said, negative findings, please don't be afraid. I mean, I've been there. My first steps in research, my first research I ever did as an MD student, I had no significance. I did all kinds of gymnastics. The p-value wasn't significant, and I was traumatized, like, oh, I'm surely going to fail. All my classmates have clean p-value this, p-value that. Then I went back to read, what is even this p-value nonsense that's traumatizing me that much? And I realized that it's just something we set by, just something that's been established and go by it. And I defended my data. I had very good mark. I defended it well. Say, okay, I didn't find this, but the trend of what I have, okay, suggests that this could be this and this and this, and it's worth looking into. And also, like Dr. Kate said, I have negative findings published. Like, you give your hypothesis that I expect this and this and this, and you actually find the opposite. We publish that so that other researchers should know that they should not go looking for that again, because that thing that you're looking for, that idea that I also had myself, that is what this is where it led to. So no need for you to go repeat it to prove a point. You need to publish it for people to know that it's been tried before and that was the outcome. So don't be scared of that. All right, I am checking the chats. Is there any other?
No other specific question. Is Ade was just meant, please don't forget to drop the research guideline. Yeah, I'm going to share the brief. We talked about setting a brief or a research agenda. I'm going to share that. I'm going to share the different slides and the different presentations that we've had since morning. Yes, Ines, your question to Dr. Siwe.
Thank you very much for this amazing presentation. It was very enriching. Please, I have a question. During our research project, we used to have a practice which of increasing the number of controls in order to increase the overall number of sample of our population. So I want to know if it is a good practice or not, because the objective for that was to make it, for example, if initially we have one case for one control, we now have one case for two controls or one case for three controls. So I would like to know if it's a good practice or not. Thank you.
Okay, thanks for the question. It's allowed. You can have controls in terms of multiples, a number of cases. Usually it's 1-to-1, but it can be 1-to-2, 1-to-3. It's allowed, and yeah, it should give you good results. Now the goal should not be to meet a certain sample size, because case control studies generally give you a minimum sample size for number of cases and minimum sample size for number of controls. All right, so you can't use one category to complement the other or to kind of boost up a little bit the overall sample size. If that's the aim, I mean, it wouldn't really work out. But if I have a case control study, I calculate my sample size, it says minimum 50 controls and minimum 50 cases. I can find 50 cases and put 100 controls. That would mean 1:2, 1 case to 2 controls. That's okay. But it should be multiples. It should be exact multiple. It should not be 1 case to 1.5 controls, for example. That would be problematic in analysis. But it could be multiples, 2, 3, 4. It's allowed. But make sure you have met the minimal sample size for each group first. You can't use cases to complete the controls sample size. You can't use controls to complete the cases sample size. Okay. So sample size studies in particular, case control studies in particular, you calculate sample size, it tells you per group. It doesn't give you a big sample size like, okay, for this study you need 1,000 people. No, it will tell you need minimum 500 for cases and minimum 500 for controls, and then you can work from there.
All right, thank you.
Yeah,
that's important, and that brings the relevance of calculating your sample size, especially, and your sample size, all of that. It goes back to the question. It goes back to the primary outcome variables. It goes back to the statistical methods used, and I mean, today we are not talking about research methods and research design. We were assuming that most of you who are joining have already carried out some form of primary research, but we just want to give you skills on how to transform that rapidly to a paper. But at times, even at this stage, even if you've written your thesis, you've written your dissertation, at times before you publish, you didn't carry out best practices in terms of statistical analysis. You might want to go and reanalyze your data in the light of most of the things that you've heard today.
yeah.
Probably you had a skewed data and you were analyzing it parametrically and things like that. Before you publish, it warrants that you go back and reanalyze your data and make sure that it fits corresponding models. Dr. 𝐒𝐜𝐴 did not go as far as getting into some of the statistical assumptions behind the different tests. All of that can be very complicated, but basically just knowing the framework of what to do with what kind of data is very important to push you forward in your quest to get your paper out. I'm going to call Dr. Brian Tegomo, who has also joined us in the course of this meeting, and who I know is also growing rapidly in publication and in peer reviewing, of course, to give us some insights with regards to and comments with regards to what he has heard so far and the questions.
Yeah, thanks a lot, Katya, and it's really great to join you guys. I'm really, really very grateful, and thanks a lot, Dr. 𝐒𝐜𝐴. It's really good to see you again, and many of us over the years have learned so much from you, and very, very grateful for all the impact that you're having in Cameroon in terms of capacity building. And thanks a lot for some names that I do recognize in the hall. Thanks a lot so much from joining. I just wanted to share a few comments from a reviewer's perspective. I have had an opportunity or the privilege to be in quite a few major journals. I will list the Lancet. I can't go into specifics about what kinds of studies they were, because some of these studies were very important, have changed the practice of how maybe COVID-19 treatments are being done. JAMA and clinical infectious disease, emerging infectious disease. One of the key questions we are constantly asking ourselves is, what is the value added of the paper? So as you're thinking about building your thesis from a thesis paper to an actual publications, what are reviewers, and I do sit on the review board. I'm a deputy editor for the Rapid Reviews journals as well. And one of the key questions we keep asking ourselves is, what is the value added of the paper? So I think Dr. Kadi talked about the importance of coming up with a research question. The kinds of statistical analysis you will have to run will have to be determined by the research question you're trying to answer. So being very rigorous and very specific on what specific questions you're thinking about and what sorts of studies are necessary to align with that specific research question is very critical. That's a key question we are looking for. When we have a preprint or a manuscript that has been submitted, the very first question we are asking ourselves is, what is the question? What is the answer? And how do the authors go about answering that question? So the method section, and the method section is a very key component of any paper, because that's where the scientific rigor of a paper is actually elaborated and really well established. So think about ideas that are, innovative, or think about something that is useful, and just the importance of making sure that it fills a gap, thinking about that aspect as well. There is a famous author who said, you don't write because you want to say something, you write because you have something to say. So think about this all the time. You don't write because you want to publish, you write because you have learned something that is new, you've learned something that is useful to people, and you want people to read your study because you've thought about this. There are a few places to, and doing a thoroughly short review is very important, because it gives you an idea of what is really out there, to know whether or not a study is new, to know if it's true, and to know if people would care. Sometimes you might do a study that people actually don't care about, and has no impact, has no use in the real world. It doesn't really fill a gap, and might suffer from multiple rejections from journals and things like that. So those are things to think about. And how do you know if a study is new? How do you know if something is innovative? How do you know if something actually fills a gap? The part about, and I'm sure Dr. Kati has talked about this, is the use of this search engines like PubMed. I'm sure he's probably elaborated on this, and Google Scholar, and using other search engines. But another really key component is talking to a subject matter expert. So someone who has documented, published expertise in a very narrow field is a very good person to talk to. These people might be more informed about what sorts of research gaps do exist. In my narrow field, and the area I spend a lot of my time concentrating on, pathogen genomics, I have a very good sense of what is lacking in the field, what is missing, what is new, what is innovative, and things like that. So speaking to a subject matter expert, it's something that is really very critical as you're thinking about what sorts of research questions you want to answer. Want to talk very briefly about a very important thing too about data source. I think having very secure data and how you go about collecting that data is a very, very important subject. And it's a question we ask ourselves a lot about the validity of a data source and where the data is coming from, and if it was collected using appropriate means. However you're doing it, if it's a survey, if it involves human subjects and things of that nature, I think it's very important to ensure that the validity itself meets the standard requirements for the study. Dr. Siwa has shared a lot about the statistical analysis. I don't think I have any particular comment in that at all. I myself learned many of the basis of statistical methods from Dr. Siwe, so I've been a beneficiary of his knowledge and wisdom myself. But one thing I would add is it's becoming more and more important to pick up statistical analysis skills. Things like using how to use some tools like R, and I know many people are using SPSS and APM4 and Excel, but the ability to use reproducible data. If you're sending a submission to a journal like Science, they will frequently request for you to have code that is reproducible. The authors will want to rerun your code on their local computer and see how it works. So I know it may be a little bit too late if many of you are very well advanced in your thesis writing already, but the ability to use code that is reproducible is very important. A few people from Cameroon have reached out to me about analyzing their data and things like that, and writing reproducible code you can share with some other person, and they can rerun those codes on their computer without actually needing to have access to your data. Reproducible examples is something that is very critical. So I think those are the key things I wanted to share. And the key things I wanted to share, a code will help you to clean the data, but it really helps you to build tables and build figures and things of that nature. And tables and figures are critical because that's what people see. I tend to look at figures first. When I have a paper, I read the title, something I might be interested in reading. It's usually the title and the figures, the figures typically would present the distribution or display trends and things of that nature, patterns of relationships between different variables, what Dr. Siri was talking about. But also the tables have the data compiled in a very simplified format and makes it a little bit more visually appealing to an audience. So yeah, so I think those were the key comments I just wanted to add. I think a lot about the research question. I think that's very important, and how you really go about answering that question is in the method section is really very very important, because the scientific rigor of every paper is well elaborated within the method section. Dr. 𝐒𝐚𝐫𝐬𝐬, thanks a lot for organizing this. I think this was very, very exciting, and thanks a lot for this idea. I think it's really going to help the research community in the long run. Thanks a lot so much. Appreciate it.
Great. I don't know, I'll pick on Dr. Siwe again. At the moment, what do you use frequently for your statistical analysis? Which software are you working on?
I work with R.
You work with R?
Yes.
That's
the main.
That's good. I know Brian is also an advocate for R. So I think probably we should do something on R at some point.
Yeah,
because R is open source, it's free, anybody can get it.
And it's fast growing.
Yeah,
there are packages for literally everything.
Edwin has put in the chat that he uses Stata. I use Stata a lot at the moment, but R, it's open source, and yeah, Stata is paid. So Edwin must be a very rich guy to be able to use Stata all this while.
Yeah, I'm sorry for interrupting, Kadi, and didn't mean to interrupt you. I think Stata is great, but the issue and SAS and all of these require you to have an institutional affiliation, and it's very expensive to purchase. And R is growing. The user community for R is so huge, and it's open source, like Dr. Siwe mentioned. So the ability, you don't have to pay for it. Definitely there are issues around data security around that still have to be resolved. But the fact that you can have code and share that with multiple people and have people look at your code and have the ability to run it on your computer is so critical. So the user base for R is growing so rapidly. I think everyone should pick up skills in R if you can, even if you're learning another language.
Exactly. So basically, that's the point I was making when I used Edwin. So yeah, so if you can learn R, and that's why I said we should probably do something on R at some point to try and capacitate people, young researchers at our level, those who are even lower than our level, to be able to pick up these skills and to be able to run their analysis on their own. Certainly, as you mentioned, the more and more journals are requiring people to upload data sets. The more and more, I think increasingly is going to become common practice as we go deep, probably into this decade, where people will not just publish just anything. They would like, okay, can you send us your data set and your codes so that we actually do them on our site? And you mentioned, rightly so, as a reviewer, that once a paper comes to you, you go straight into the figures and the tables. And so the next thing we'll be talking about display items, how to build display items. But before we go into display items, I don't know if there is any last burning question to Dr. Siwe. Siwe. I would take the silence in the room to be a resounding no question. So thank you so much, Dr. Siwe. I think I've added the first 3 presentations into the chat. I think I'm just going to add an example of a brief as well, which we built for 2 papers in Cameroon, which you can just use as templates to build your own personal research writing agenda or to set your research brief. And of course, then you can use those papers as well. And if not, we're going to go into display items. It's going to be really short, and then Brian will come in again, and where I will just Q&A him on some other things regarding his journey into research, just to inspire us again, as we heard from Aguns a while ago. So